This is Lesson 9 in our Calculus 3 series, Vector-Valued Functions. A vector-valued function or vector function of the real numbers assigns a vector to each number in R. So that looks like R of t, notice the vector hat over R here, R of t in component notation looks like f of t, g of t, h of t, or in standard basis notation looks like f of ti plus g of tj plus h of tk. So each component is its own real valued function. And together it comprises a vector. Now we've already seen the idea of a position vector. When we were talking about the equation of a line, we saw a position vector r that went from the origin to a point on the line. Now let's take a look at r as a vector valued function. We know that in component notation, r looks like x, y, z, where x, y, z, point P, is a point on the line. We also have, by the parametric equations for the line, x is equal to x naught plus at, y is equal to y naught plus bt, and z is equal to z naught plus ct. So really we could think of r as r of t, a vector valued function, and this x is a function of t, so we can think of this as x of t, y of t, z of t. And so r of t, the position vector, gives us a vector starting at the origin and ending at a point on the line. For any point on the line, r of t is the vector from the origin to that point. And for any t in the real numbers, r of t gives the vector from the origin to the point on the line. And this defines it to be a vector-valued function. We're saying for every real number, t, we're getting a vector here. Now let's take a look at an example. Sketch the curve defined by the vector function r of t is equal to cosine t, 2 sine t, radical t. Now for every real number t for which these functions exist, we're getting a vector, and this is going to be a position vector, so it's a vector from the origin to a point in space. And the collection of all of those points is going to make up a curve in three-dimensional space. So r of t is the position vector. It's always going to be a vector, but it's a vector that goes from the origin to that point in space, and we could think about the collection of points that we get that come out of these functions x, y, z. So x of t is equal to cosine t, y of t is equal to 2 sine t, z of t is equal to radical t. For every t value that we have, we're going to get a point in space defined by these functions. And r of t is going to be the vector that goes from the origin to that point in space. In order to get a sketch of this curve, we want to first have an idea of what kind of values we're going to be getting for x, y, and z. When I look at x of t equals cosine t, I know that these values are going to be oscillating between -1 and 1. So I know that for all the points on my curve, the x values are always going to be in this interval. Similarly, the y values are always going to be between -2 and 2. I also know that the z values are going to go from 0 off to infinity. But notice here, because we're dealing with radical t, we have a restriction here on our domain. We can only take t values that are going to be greater than or equal to 0. In general, the domain of a vector-valued function is going to be the intersection of the domains of its component functions. In any case, we have x values that vary between -1 and 1. We have y values that vary between -2 and 2. We have z values that go from 0 to infinity. And I want to keep in mind what this graph looks like. Z of t equals radical t. In just a zt plane, we have our half a sideways parabola, right, our radical function. So we want to keep that in mind as we're sketching our curve here in three-dimensional space. Now the first thing I want to do is plot some points. Let me take t equals 0. When t is equal to 0, x is equal to 1, y is equal to 0, z is equal to 0. Here's t equals 0, 1, 0, 0. When t is equal to pi over 2, I get x is equal to 0, y is equal to 2, and z is equal to radical pi over 2, which is approximately 1.25. So when t is equal to pi over 2, this vector-valued function is pointing to the point 0, 2, 1.25 approximately. So 0 to 1.25. Now we're here. Okay, what's next? When t is equal to pi, x is equal to -1, y is equal to 0, and z is equal to radical pi, which is approximately 1.77. X is equal to -1, y is equal to 0, and z is equal to approximately 1.77. So we're here. For t equals 3 pi over 2, we're at 0, -2, approximately 2.17. So 0, -2, approximately 2.17. And when t is equal to 2 pi, we're at x equals 1, y equals 0, and z is approximately 2.51. So we're at 1, 0, 2.51. So let me just label these. And now as we're connecting the points here, we want to keep in mind how z is changing over time. Essentially what we're doing is we're taking this curve and we're wrapping it in three-dimensional space to go along with the x and y coordinates with it. So when I go to connect my dots here, I have to keep in mind the shape of this curve. I have to start here, come up, and around. So this z value is increasing. It increases sharply at first, and then the increase slows down. It increases sharply at first, and then the increase slows down. In the meantime, x and y are oscillating. Right? We're getting that rotation because x is going from 1 to -1 and back to 1, and y is going from 0 to 2 to -2 and back to 0. And so this is going to keep, as time goes on, this is going to keep spiraling upward. And a computer-generated version of that graph looks like this. As you can see, it could be difficult to get accurate sketches of these kinds of curves. So while you might not become a pro at sketching them yourself, you should be able to match up curves with their vector-valued functions. So let's take a look at an exercise like that. We want to match our vector-valued functions to their graphs. So we're going to start with these four functions. We've got these two graphs here, and we've got a couple more to look at as well. Now, where do we start when matching up these graphs and functions? Well, just like when we started our own sketch, we wanted to look at each of the component functions and get an idea of what kind of values were going to come out of there. So for example, with function a here, t cosine t, we notice that there's no bound on the values that we're going to get for x. Same for y. There's no bound on the values that we're going to get for y or for z. So for example, a is not going to match up with this first graph because clearly the x and y values in this first graph are bounded. So what we're expecting here is something like a cosine and a sine for x and y. So it looks like this first graph would have to be b or d. And we'll talk a little bit more about that in a second. But notice in function c, we have that our x values are oscillating, but our y and z values are unbounded. This graph has x values that are oscillating, but our y and z values are unbounded. So it looks like this is going to be function c. Let's take a look at the other graphs as well. Again, we said we have x oscillating, y and z are not. Here, we have z oscillating. We can see the height of this curve is oscillating. So this definitely does not belong with function c. And here we can see unboundedness in x and y and z. So this graph is going to be function c. We have x of t equals cosine t. That's oscillating. But we have y of t and z of t unbounded. Let's take a look back here. We said this graph has z oscillating. Which one of these functions has a z-coordinate function that oscillates? Only function d. This must be the graph of function d. So far we're left with functions a and b. Well, earlier we said that this graph must be either b or d. And we can see here that we have bounded x and y values, bounded by -1 and 1, both of these x and y values. And what's happening with the z values here? Let's just make sure this matches up. What happens when t is equal to 0, for example? When t is equal to 0, we're at the point 1, 0, 5. 1, 0, 5. That's going to be this point up here. And then what happens as t gets bigger? As t gets bigger, this z value shrinks exponentially. It gets small really fast. And in the limit, it goes to 0. So we have these z values that are going towards 0 as x and y continue to circulate. And so we're left with graph A here, and let's see why this makes sense. We can see that our x and y values are oscillating, but they're also growing in size. They're not bounded. So we have a t cosine t. We get the oscillation from cosine, but we get the unboundedness from this factor of t. Same thing in the y. We get the oscillation from the factor of sine t. We get the unboundedness from the t. And then our z values continue to grow linearly. And so that's the graph of function A. Now let's take a look at this example. Find a vector function that represents the curve of intersection of the cone z equal radical x squared plus y squared and the plane y minus z equals -2. First thing I want to mention is that when we were talking about our quadric surfaces, we had cones in the form z squared equals x squared plus y squared. I just want to point out that with this equation, we're talking about just the top part of the cone. And so let's take a look at what the intersection of this curve and this plane look like. Here's a 3D plot of the cone and the plane. So let's just take a look at it. There's our cone and our plane slicing through. From the bottom, turn this around a little bit, we've got our cone and our plane slicing through. So now what shape is that curve that we're expecting? Looks like a parabola, the curve of intersection. Now we want to find a parametrization for that curve of intersection. We're looking to find x equals x of t, y equals y of t, z equals z of t, functions that describe the set of points, and then we're going to talk about the position function or the vector function, r of t, with those component functions. So we want to start by eliminating z and finding a relationship in x and y. And so we're going to set radical x squared plus y squared equal to y plus 2. Square both sides, simplify, our y squareds cancel, and we get x squared is equal to 4y plus 4, or y is equal to x squared over 4 minus 1. So now we have a relationship between x and y. So we could let x equal t, and then y would be t squared over 4 minus 1. And then so far, we would have 2 of the 3 functions we need. Because remember, we're looking to parameterize the x, y, and z coordinates. So if x is equal to t and y is equal to t squared over 4 minus 1, then we just have to plug into z either of these functions, right? Z is equal to y plus 2. That gives us t squared over 4 plus 1. So r of t is equal to t, t squared over 4 minus 1, t squared over 4 plus 1. And this is one possible parametrization for the curve of intersection. And this parametrization was based on our choice to let x equal t and then go from there. And that curve looks like this. And that's the curve of intersection that we're looking for. Now let's talk about limits and the derivative. For our vector function r of t equaling f of t, g of t, h of t, the t values are real numbers, so we could talk about t approaching a. And then what does that mean in terms of the components? Well, it means exactly what you would think. It means that this is the limit as t goes to a of f of t, the limit as t goes to a of g of t, and the limit as t goes to a of h of t. Essentially, we've got three functions and we're just grouping them together as a vector. And so when we talk about limit as t goes to a of the entire set of functions, it's happening to each component function. And then with that definition of limit, we can talk about a derivative. We can talk about vector function r prime of t being the limit as h goes to 0, r of t plus h minus r of t over h. And as you would expect, our component functions for the derivative are then f prime of t, g prime of t, h prime of t. And of course we could use the other notation as well. Then for a vector function describing a curve in three-dimensional space, like we were just looking at before, say r of t is x of t, y of t, z of t, then r prime is going to be dx dt, dy dt, dz dt, and let's think about what this means. This is the rate of change of x with respect to time, the rate of change of y with respect to time, the rate of change of z with respect to time. This is very useful information. At any point along our curve, if we know the t-value that got us to that point, we have a vector in the direction of where this curve is headed. We know how x is changing, how y is changing, how z is changing. So actually what r prime of t gives us is a tangent vector to the curve at a particular point. So at any particular t0, when we evaluate these derivative functions at t0, we're getting a tangent vector to the curve at that point. So let's take a look at the parabola that we had above. This was the curve of intersection of the cone and the plane. And what's r prime of t? Derivative of t is 1. Derivative of t squared over 4 minus 1 is 2t over 4, or t over 2. Similarly for the z function, t over 2. So when t is equal to 0, our position is given by r of 0, which for this parametrization is 0, negative 1, 1. 0, negative 1, 1. That's this point right here. That's when t is equal to 0. And what's r prime of 0? R prime of 0 is 1, 0, 0. And that's our tangent vector to the curve at that point. So starting with negative t values, our curve is coming from the back, turns at this point, and comes back forward. And at that turning point, its direction is 1, 0, 0. And keep in mind that if we had a different parametrization for this curve, the tangent vector might have different length. It'll be the same direction at the same point on the curve, but it might be scaled differently based on the different parametrization. So instead of 1, 0, 0 as a tangent vector, we might have a scalar multiple of that with a different parametrization of the same curve. We could even go one step further and find the equations of the tangent line to the curve at that point. Find parametric equations for the tangent line to the curve of r of t at t equals 0. So I'm still talking about the same curve, r of t. We know that that point is 0, negative 1, 1. That point is 0, negative 1, 1. And we now know the direction is 1, 0, 0 when t is equal to 0. So we have a point and a direction vector for our line, and we can just plug in x equals x0 plus at, y equals y0 plus bt, z equals z0 plus ct. And that simplifies to x equals t, y equals negative 1, z equals 1. And as a line, that looks like this. That's our tangent line. Now for the first curve that we sketched, let's find a tangent vector there. In fact, let's find a unit tangent vector there. So for the curve of the vector function, r of t equals cosine t, 2 sine t, radical t, find a unit tangent vector at t equal pi over 2. Well, what does it mean to be a unit tangent vector? It means it needs to be a unit vector. So we need to find a tangent vector and then scale it so that it has length 1. So here's our derivative function, r prime of t, negative sine t, 2 cosine t, 1 over 2 radical t. And at t equals pi over 2, we plug in and we've got negative 1, 0, 1 over radical 2 pi. So when we first plug in, it looks like this. I did a little work to simplify that. You can follow the work over here. Rationalized, simplified, and that comes to 1 over radical 2 pi. So this so far is our tangent vector, but it's not a unit vector. So let's find its length, and then we can scale it to be a unit vector. Finding the length, we have negative 1 square plus 0 square plus 1 over radical 2 pi square. So we're here. And now we're going to scale our vector by dividing by that length. And so this is going to be our unit tangent vector. We can multiply that factor in, and we're here. So let's see what that looks like on our curve. So this is our unit tangent vector at the point when t is equal to pi over 2. So we know that in total the length of this vector is going to be 1. It's going back by negative 1 over radical 1 plus 1 over 2 pi. It doesn't change in the y direction, and it has a positive increase in z. So from this point, we're going back in the x direction and up in the z. And that's going to be our unit tangent vector. And we'll conclude our lesson here on vector-valued functions.